Hello friends, I welcome you in lecture number 18 on graph theory. From previous lecture, we are familiar with the concept of connected graph now. A graph in which there is a path between any two distinct vertices is called a connected graph. So in this lecture, we are going to discuss about cut vertex or articulation point. We are going to discuss that when a vertex of a given graph is a cut vertex, another name is articulation point, and some authors call it as cut point of a graph also. So first we take one example to understand the definition of cut vertex. Suppose I consider this graph which is connected with these edges. Suppose vertices are denoted by V1, V2, V3 and V4, and it is clear that this graph is connected. If we take any pair of vertices, then they are reachable from one another. Any two vertices which are distinct are reachable from one another, or for any two distinct vertices there is a path between them. So this is connected graph. Now what happens if I remove one vertex, say V1, and the edges incident with V1? Here there is only one edge incident with V1, so I am removing vertex V1 as well as edge containing V1 or edge incident with V1. So after removing V1 and all edges incident with V1, we obtain subgraph of given graph, and this subgraph is also connected. If I remove vertex V1 and edge containing V1, then I obtain a connected subgraph. So in that case V1 is not a cut vertex, because after removing V1 and all edges incident with V1, we obtain connected subgraph. So we try for vertex V2. So let me first come back to the original graph. Suppose I let me write V1 here. So now instead of removing V1 and all edges incident with V1, we try to remove V2 and all edges incident with V2. So there are two edges incident with V2, so we remove them and we remove vertex V2 also. So now what we have obtained, after removing V2 and all edges incident with V2, we obtain this subgraph which is now disconnected. This subgraph is not connected because if we consider these two vertices V1 and V3, then there is no path between V1 and V3. So after removing a vertex V2 from a given connected graph, we obtain disconnected subgraph. Or after removing vertex V2, our graph, original graph, transforms into disconnected graph. In that case, we say that vertex V2 is a cut vertex. So if we have a connected graph G, and after removing some vertex V from that connected graph, whatever graph we obtain, that is G minus V, if that graph is disconnected, then that vertex is called cut vertex. Similarly, we can check whether V3 and V4 are cut vertex or not. So for that we again sketch the original graph. Let me again draw this vertex V2 and edges incident with V2. Now if I remove vertex V4 and edge incident with V4, then I will obtain connected subgraph. So V4 is not a cut vertex. So let me try for V3. let me come back to the original graph. This is original graph. Now I am considering vertex V3 and I am trying to remove edges containing V3 and vertex V3 itself. So there are two edges incident with V3, so we remove them first and we remove V3 also, and whatever we obtain, that is a disconnected subgraph. There is no path between V2 and V4 as well as between V1 and V4. So V3 is a cut vertex, because after removal of V3 and all edges incident with V3, we obtain disconnected subgraph. So here we have seen that V2 and V3 are cut vertices and V1 and V4 are not cut vertices. So remember, if we have a connected graph, say G, suppose G is a connected graph and V is an vertex of G. Now if we remove vertex V and all edges incident with V, then we obtain this subgraph G minus V. So if this subgraph is disconnected, then this vertex V is called cut vertex. Now if our graph is not connected, then also we can talk about cut vertex. Suppose I have this graph V1, V2, then V3, V4. Suppose I have V3, V4, V5. Suppose this is our graph G, and graph G itself is disconnected and it has two connected components. This is one connected component, this is another connected component. So if our graph is not connected, then also we can talk about cut vertex. In that case, if after removing a vertex and all edges incident with that vertex, if the number of connected components are more than the original graph, then that vertex is called cut vertex. Suppose I consider vertex V5 here. If I remove vertex V5, then I will have two connected components. So in that case, vertex V5 is not a cut vertex, because original graph also has two connected components. So let me come back to the original graph. Okay, fine. So now I try to check for another vertex. Suppose I remove vertex V2 and edges incident with V2, then also there are two connected components. So V2 is not a cut vertex in this case also, because after removing V2, the number of connected components we obtain is 2, that is the same number for the original graph. Suppose I consider removal of vertex V4. Suppose I remove vertex V4 and edges incident with vertex V4. Then you can see now I have three connected components. One connected component is this one, another is this one, another is this one. So after removing V4, we obtain three connected components which is bigger than the connected components of given graph. Given graph had two connected components, and after removing vertex V4 and all edges incident with V4, we obtain three connected components. Therefore V4 is a cut vertex. So whenever we have connected graph, then cut vertex means after removal of that vertex, whatever graph we obtain, that is disconnected. And if our original graph is disconnected, then cut vertex means after removal of that cut vertex, whatever subgraph we obtain has more connected components as compared to the connected components in a given disconnected graph. So I hope this is clear now. I have written the definition. They sometimes ask you to write down the definition of a cut vertex. So here I have written, in a graph, sometimes the removal of a vertex and all incident edges produces a subgraph with more connected components. Such vertices are called cut vertices. This is general definition. If our graph is connected graph, then it has only one connected component, that is graph itself. And after removing some vertex, if graph becomes disconnected, that means graph has two components. So in that case also V is a cut vertex. And if graph is given graph is disconnected with say two components, and after removal of some vertex we obtain three or more disconnected subgraphs, then in that case we have three or more connected components and vertex V is called a cut vertex. So this is the definition of cut vertex, and you can find out the cut vertex of a given graph by removing that vertex as well as all the edges containing that vertex as endpoint. So again I read this definition. In a graph, sometimes the removal of a vertex and all incident edges produces a subgraph with more connected components. Such vertices are called cut vertices. This is important. Whatever subgraph we obtain has more connected components as compared to the connected components of given graph G. If given graph G has n connected components, then whatever subgraph we obtain after removing a vertex and all incident edges, that subgraph must have more than n connected components in order that removable vertex is a cut vertex. Here we have one graph which is connected, and we can decide that which vertex of this graph is a cut vertex. Suppose we check for vertex A. Suppose I want to check whether vertex A is a cut vertex, then what I will do, I will remove edges containing vertex A and vertex A itself. So now I have removed all the edges containing vertex A and vertex A itself, and whatever subgraph I obtain is a connected subgraph. That means vertex A is not a cut vertex. So let's come back to the original graph. Similarly, if we consider vertex B, if we remove vertex B and all edges incident with B, then whatever we obtain, that is also connected subgraph. Therefore B is also not a cut vertex. So in this way you have to check for each and every vertex to determine whether it is a cut vertex or not. Now we check for vertex C. Vertex C is end point of these four edges. This is one edge, another edge, 1, 2, 3 and 4. So I have to remove these four edges and vertex C. So let me remove this edge, this edge, this edge, this one and vertex C. Now you can see after removing vertex C and all edges incident with vertex C, we obtain two connected components. Our given graph becomes disconnected after removing vertex C and all edges incident with vertex C. That means vertex C is a cut vertex, or it is a articulation point. Vertex C is a cut vertex for this graph. So let's come back to the original graph. Just a minute. This is taking a time, but that was the meaning of cut vertex. Okay, fine. So we are to the original graph. Similarly, you can check that if I remove vertex D and all edges incident with D, I will obtain this subgraph. If I remove vertex D and all edges incident with vertex D, I will obtain this subgraph. Here I have F, this is E. So there are two edges incident with D and we have removed those two edges and we obtain this subgraph after removing vertex D and edges incident with D. So this subgraph is connected, therefore D is not a cut vertex. Similarly, you can check that vertices E and F are also not a cut vertex. D is also not a cut vertex. E and F, you can check, they are also not cut vertices. So there is only one cut vertex for this graph and it is C. Vertex C is a cut vertex. Some authors write the definition of cut vertex in this way also. They define cut vertex for connected graph. Suppose G is a connected graph, then a vertex V in G is called a cut vertex if G minus V is disconnected, and G minus V is the graph obtained from G by deleting vertex V and all edges containing V. Here we have taken one another graph and you can try to find out cut vertex for this graph. So you can check that if I remove vertex A and all edges incident with A, let me remove these two edges incident with A and vertex A, then graph remains connected. Therefore A is not a cut vertex. So let me try for another vertex. Let me come back to the original graph. So similarly, you can check for vertex B. If you remove this vertex B and these two edges, whatever graph you will obtain, that will remain connected. So I am trying for vertex D. Let me try for vertex D. So vertex D has 4 edges incident with it. So I have to remove these 4 edges and vertex D. So I am removing this edge, this edge, this edge and this edge and vertex D itself. So after removing vertex D and all edges ending or meeting at D, we obtain a disconnected subgraph. Therefore vertex D is a cut vertex. Vertex D is a cut vertex because after removing vertex D and all edges incident with D, we obtain two connected components, or we obtain two subgraphs which are connected. So therefore D is a cut vertex. So we come back to the original graph. Let me try to come back to the original graph. This is not working, just a minute. So I am pressing Ctrl Z on my PC and I am trying to come to the original graph. So it will take a second, just a minute. So this was the original graph and we see that after removing vertex D, we obtain two disconnected, two connected subgraphs, or we find that original graph becomes disconnected after removing vertex D. So in this way we can find out cut vertices of given graph. You can try for this remaining vertices E, H, F all, and you will find that there is only one cut vertex for this graph, and that is vertex D. So sometimes they ask you to define cut vertex and to find out the cut vertices for given graph. So this is all about this session. In this session we have defined cut vertex for connected as well as disconnected graph. If our graph is a connected graph, suppose G is a connected graph, then a vertex V in graph G is called cut vertex if after removing vertex V and all edges incident with V, whatever subgraph we obtain, that is disconnected. If G minus V is disconnected, then vertex V of a connected graph is called disconnected. Now suppose our graph itself is disconnected, then it will have two or more connected components. Suppose graph has n connected components. Suppose we have a disconnected graph with n connected components. Now suppose after removing some vertex V and all edges incident with vertex V, whatever subgraph we obtain, if that subgraph has more than n connected components, then vertex V is called cut vertex. If after removing vertex V, whatever subgraph we obtain has more connected components as compared to the connected components of given disconnected graph G, then V is called cut vertex for disconnected graph. So this is all about this session. I hope you like it. Thanks for watching.